Hello, my name is Eric Maynard. For my 112 term project, I used Neuroevolution to create an artificial intelligence user for the game of Mario. Right here is our splash screen. Not very aesthetic. The artwork is not my own, but taken from the internet. We have two options. You can either create a new population of initialized genomes to play Mario, or you can load an existing evolved population. For this demonstration, let's create a new population. And now we can configure the population. We can give it a name, 112. We can give it a population size. Let's, for all intensive purposes, give it a population size of 6. Much larger is preferred in the Neuroevolution algorithm. Node augmentation probability. This is the probability that a node will be added to the neural network. Let's just make it insanely high, like 0.5%. Which again is not ideal. And the connection augmentation probability is the probability that a connection is created between nodes each generation. So let's make that also incredibly high. And let's begin. And this brings us to the simulation screen where the Neuroevolution algorithm is actually tested. In the upper left, we have the game of Mario being played by the artificial intelligence. To the right, we have the neural network, which is controlling the Mario player, and below we have the controls. So let's explain what's going on here. To the right, we have this visualization of what the computer actually perceives from the game. It takes away all the superfluous artwork and sprites that are unnecessary, and only looks at the important things like the platforms and the character and the enemy sprites. And it feeds that into this neural network. Well, neural network is a abstract concept that tries to mimic a biological neural network as seen in a brain. And it takes input from the screen, runs it through these abstract neurons, and sends them to different outputs, left, right, or up, that controls the character. In generation 1, the the network is initialized to having a single input neuron, 3 output neurons, with very little functionality. As the generations progress, more and more complexity is added through an evolutionary genetic algorithm. That's what those configurations determined earlier. Down here, we can pause the simulation. We can resume it. We can run our historical best. I'm not going to do that now because so far we haven't created a successful genome yet. We can graph the history of the population, which it doesn't have one yet. We can readjust the parameters to make them more effective, 0.1. Or we can do a speed mode, which if we click on it, will disable the visualization tools to increase the rate of testing, and it significantly increases that speed, I think up to like 10 times. So if we click it for 10 minutes, it will cycle through all the genomes. Let's exit out of that. We can also load a population for memory. Here's one that I evolved earlier. We can load it. And as you can see, this one's more effective, has a more complex structure and topology. And there's some interesting things we can see about this. We can run the best genome from the population, and this is the one that beats the level. Watch it go. And we can also graph the history of this population, and we can see over the generations the increase in fitness of the population as a whole. And you can kind of see bands running through each generation, and this is not by accident. It's representative of the speciation component of the algorithm. So how genetic algorithm works is creates a population, tests them in the simulation, and then gives it a fitness score. And then the genomes with the highest fitness are mated to get bred together to produce the next population. However, the problem with using this for neural networks is that a lot of the innovation is lost or not protected when a new node is added to the network, because it kind of takes away from functionality initially. Another way to protect that is to speciate your genomes and protect each species. So when a genome is created with a differing topology from the rest, it's added to its own species and protected by the fitness algorithm. So you can see that there are some species that are banded together, and genomes that are banded together, that aren't as effective as the others, but are still part of the population for an extended period of time. You'll also notice that there are certain points in the level where the population could not get past for a number of generations, but eventually it does overcome and move on. So this is my 112 term project. I hope you understand it and thought it was interesting. Thank you for your time. Bye.